There is an ocean that aviation regulators, meteorologists, and deep-sea engineers describe using the same word: unknown. The southern Indian Ocean, the stretch of deep water between the southern tip of Africa, the coast of Antarctica, and the western edge of Australia, is the most remote, the least mapped, the least understood, and the most hostile aviation environment on the surface of the Earth. Aircraft crossing it are out of radar contact for hours at a time. Satellite communication is degraded over its most remote sections. The ocean floor beneath its deepest corridors has been mapped in less detail than the surface of Mars. Since the beginning of commercial aviation, approximately 75 aircraft have been lost over or near the southern Indian Ocean without full explanation, meaning investigators closed their reports with findings that accounted for the probable cause. But the physical evidence, the wreckage, the flight recorders, the definitive confirmation, was never recovered. They are still down there, in water so deep, so cold, and so physically hostile that the most advanced underwater search technology humanity has ever deployed has failed to find them. This is not because we are not looking. It is because this ocean does not want to be understood, and the physics of why are stranger than most people have been told.
The southern Indian Ocean sits between 30 and 60 degrees south latitude, a band of ocean that sailors have called the Roaring Forties, the Furious Fifties, and the Screaming Sixties for 3 centuries. These names are not poetry. They describe the physical reality of a region where no significant landmass exists at these latitudes to interrupt the atmospheric flow, allowing weather systems to build in intensity for thousands of kilometers before encountering anything solid. Wind speeds in the Furious Fifties regularly exceed 80 knots. Wave heights of 15 to 20 meters, the height of a 5-story building, are not unusual. Atmospheric pressure gradients in this region change faster than anywhere else on Earth, creating weather systems that can go from manageable to catastrophic in hours. Commercial aircraft crossing the southern Indian Ocean at cruise altitude are above the weather, but their search and rescue zones, if something goes wrong, are within it. The average sea state in the primary search corridors used during the MH370 search was sea state 5 to 6, significant wave height of 2.5 to 4 meters, on good days. This is the environment in which search vessels were operating for years, looking for an aircraft that has still not been found. But the weather is only the first layer of what makes this ocean different from every other.
The second layer is acoustic. The deep ocean contains a phenomenon called the SOFAR channel, sound fixing and ranging channel, a layer of water at a specific depth where the combination of temperature and pressure creates a velocity minimum for sound propagation. Sound waves entering this channel are trapped within it, able to travel thousands of kilometers without significant attenuation, across entire ocean basins from one hydrophone station to another. The global network of hydrophone stations that monitors this channel was originally built during the Cold War to detect Soviet nuclear submarine activity. After the Cold War, many of these stations were repurposed for scientific monitoring, and they have been continuously recording the acoustic signature of the southern Indian Ocean ever since. When MH370 disappeared on March 8, 2014, acoustic analysts spent months searching this hydrophone data, looking for the impact signature of a large aircraft striking the ocean surface at high speed. They found signals. Multiple signals from multiple hydrophone stations were identified as potentially consistent with an aircraft impact. None of them could be definitively confirmed as MH370. Because the southern Indian Ocean is acoustically active in ways that create exactly the kind of signals an aircraft impact would produce from completely natural sources: underwater earthquakes, submarine landslides, ice calving from Antarctic glaciers, biological acoustic events from marine life that we have not yet fully characterized. The ocean floor in this region is acoustically so complex that the most sophisticated passive acoustic analysis systems ever built cannot distinguish with certainty between an aircraft impact and a natural geological event. This is not a technology limitation that will be resolved by better computers. It is a fundamental ambiguity built into the physics of this specific ocean.
The MH370 search became the most expensive aviation search operation in history, costing over $200 million across 3 years of active operations. It deployed technology that had never been used for civilian aviation search before, the Bluefin 21 autonomous underwater vehicle, capable of operating at depths of 4,500 meters, generating acoustic sonar imagery of the ocean floor with resolution sufficient to detect objects the size of an aircraft component. The GO Phoenix, Fugro Equator, and Fugro Sentinel, specialized deep-water search vessels equipped with towed sonar systems capable of imaging the ocean floor at depths of 6,000 meters. They searched approximately 120,000 square kilometers of ocean floor, an area the size of Pennsylvania, at depths averaging 3,500 to 4,500 meters, in water whose temperature is approximately 2 degrees Celsius, under surface conditions that frequently required search vessels to suspend operations due to weather. And they found nothing that could be identified as MH370, not because the technology failed, because the ocean floor in the southern Indian Ocean is not the flat, featureless plain that aviation search planners had historically assumed. The Broken Ridge, the Zenith Plateau, the Perth Abyssal Plain, a landscape of underwater mountains, deep canyons, sediment plains, and volcanic ridges, all of it unmapped in useful detail before the search began. The search teams were mapping the ocean floor for the first time while simultaneously searching it for an aircraft, an exercise comparable to searching for a specific building in a city whose maps had never been drawn. The bathymetric data collected during the MH370 search represents the most comprehensive deep ocean mapping ever conducted in the southern Indian Ocean. It revealed features that had never been documented, an entire underwater geography that changed every subsequent calculation about where the aircraft might have come to rest. In January 2018, the Australian Transport Safety Bureau formally suspended the MH370 underwater search. The official statement noted that the aircraft had not been located within the searched area, and that locating it would require either new information or a new search area. In January 2023, a private company, Ocean Infinity, proposed a renewed search using a fleet of autonomous underwater vehicles operating simultaneously, 8 AUVs deployed in parallel, each capable of independent operation, collectively able to search an area 3 times larger per day than the single vehicle searches of the previous effort. The Malaysian government has been in negotiation about this proposal since 2023. As of the time of this video, MH370 has not been found. 71 million cubic meters of ocean have been acoustically imaged. Debris confirmed as MH370 has washed ashore on the eastern coast of Africa and the islands of the Indian Ocean, confirming the aircraft entered the southern Indian Ocean, confirming it is down there, somewhere, in the 120,000 square kilometers already searched, or the larger area that has not yet been reached. But here is the physical reality that the search has revealed, not about MH370 specifically, but about this ocean generally. The southern Indian Ocean is the single largest uncharted geographic environment remaining on Earth. More of its floor is unmapped than any comparable area of the planet's surface. Its acoustic environment is incompletely understood. Its weather systems are imperfectly modeled. Its deep currents, the ones that determine where floating debris goes, and therefore where a search should begin, are less well characterized than the atmospheric currents of other planets we have sent spacecraft to study. Aviation transits this ocean every day. 40 to 50 commercial flights cross its most remote sections daily, each one momentarily beyond the reach of any radar system on Earth, each one trusting a satellite communication network that covers this region less completely than any other commercial route, each one flying above a body of water whose physical properties remain, in critical ways, uncharacterized. The ocean does not hide secrets by intention. It hides them by being larger, deeper, colder, and more complex than our technology has yet been designed to handle. MH370 is down there, and the search for what this ocean does not want to reveal continues. Follow for more about the physical frontiers that aviation crosses and the gaps in our knowledge that those crossings expose.